Again, if you have questions, please go to Slack. There's a channel called track-physics-and-astronomy. I created a post there about this talk. If you have questions, please respond to that thread and ask your question there. So our next speaker is Frank Strug. He's going to talk about KvikUproot, reading and deserializing high-energy physics data with KvikIO and CuPy. Give you the floor.
Thank you. Good afternoon, everybody, and making it to the end of the talks today. Today, I would like to tell you about a project that I have been working on called KvikUproot. KvikUproot is a new addition to the uproot package and provides GPU-aware I/O into the high-energy physics analysis pipelines. I will demonstrate how I have utilized KvikIO and CuPy to interpret data in GPU memory, particularly in GPUDirect storage-enabled environments, which creates a direct data path between storage and GPU memory. Oh, got a friend. First, I would like to discuss the historical context of the high-energy physics domain-specific file formats and root. Then I will move on and briefly explain the uproot package that KvikUproot extends and how we read high-energy physics data in Python. Then I will discuss the growing challenges of larger and larger data sets and at the Large Hadron Collider and other high-energy physics experiments, and why GPU acceleration is something we are so interested in. Then finally, after we've gotten all that context, I will talk about how I have adapted the uproot workflow for GPU interpretation of raw root data, and then some of the development and performance challenges that I ran into in this path. If there is still some time, I will try and run a demo, but we might not have time for that in the end. Okay, so first, root. I would think that most high-energy physicists are very familiar with the root software package, but those outside of high-energy physics might not have heard about it. Root is the de facto standard in high-energy physics. It forms the backbone of most experiments' software stacks, and it provides a suite of tools for analyzing, visualizing, and storing experiment data. T-tree is the name of Root's first established file format, which was established in the mid-90s. T-tree was formed out of experiments' needs to store non-rectilinear data in a self-contained way. T-tree's design philosophy centers around the need for flexibility in the types of data that it can store, as well as backwards compatibility. It is very important to the reproducibility of our results that all the data that we produce, we can go back far in the past and look at it again. You can look at T-tree data that was written in the 90s in the original first iterations of Root and read them in today on modern machines in the newest versions of Root. Although initially T-tree was not very performant, it wasn't designed for that need. So over time, as this inefficient layout became more of a problem, Root improved upon it and moved to increasingly contiguous memory layouts for T-tree. However, that historical baggage was not something that T-tree could overcome, and Root decided that really they needed to start from the ground up and come up with a whole new file format for storing high-energy physics data. So just in November of 2024, Root unveiled its R-on-tuple file format, which had some major changes from T-tree. Some of the biggest changes are, one, that it moved Root from storing data in a big endian byte layout to a little endian byte layout, which matches the architecture of modern machines. It also opted for a much more simple layout of the metadata, offset, and payload data by completely separating all these components. Then, so yes, these root files can be read in by the root software stack. So how do we read that in Python if we are so interested? Root does provide a pyroot package for Python. However, root can be sort of challenging to set up for users, while it is very easy to pip install any Python package available on PyPy. So uproot is a Python library that reads root files in pure Python and only strictly depends on NumPy and the packaging libraries. And uproot is capable of interpreting all the current file formats that root has established, all the versions of T-tree that are out there, as well as the newest RNtuple format. KvikUproot extends uproot's ability to interpret data by utilizing KvikIO and CuPy to provide users the ability to interpret raw RNtuple data in GPU memory. But why do we need to get data onto the GPUs? Why is this so important to us in high energy physics? Right now, as our experiments mature and we have a need for larger and larger data volumes to push the limits of our results, total data recorded by the EOS CERN storage service passed the 1 exabyte threshold in 2023, which is already double the amount of data that was stored in 2020. And moving forward, after the Large Hadron Collider's current run 3, for the high luminosity upgrade of the Large Hadron Collider, it is expected that the CMS and ATLAS experiments alone will produce about an exabyte of data per year already in 2030. And since single-threaded CPU performance is plateauing, in order to process and analyze all this data, we need to get creative in high energy physics. So naturally, we're looking to increasing the parallelization of our workflows, as well as leaning into hardware acceleration, particularly GPUs. And from an analyst perspective, Python tools that are maturing in the CUDA space for leveraging GPU accelerators are becoming very robust and easy to use. Python users don't have to have any knowledge of CUDA programming to get the benefit of CUDA GPU acceleration. However, in the high energy physics space, there are no tools that exist yet for efficiently streaming root data from storage into GPU memory. It doesn't matter if we can analyze the data super fast if we can't get the data onto the GPU just as fast. So in enters KvikIO and CuFile. CuFile is a CUDA-specific library for performing I/O operations between NVIDIA GPUs and storage. Particularly, it has GPUDirect storage technology capabilities, which allows a direct data path to flow, for the data to flow between storage and GPU memory. So on this diagram here, we have our storage on the right, and it is connected to the GPU and the CPU via a PCI bus. When we have a GPUDirect storage enabled environment, we can then transfer that data directly from storage into the GPU via the PCIe bus without having to go through the CPU or system memory. The idea behind GPUDirect storage and the promises it makes is that this will increase bandwidth to the GPU and lower latency in I/O. And since this avoids creating a bounce buffer through the CPU is now freed for other tasks, which is very important for distributed computing setups. Fortunately, though, you can still get efficient I/O without a GPUDirect storage environment. Both QuickIO and CuFile provide compatibility modes that allow users to perform efficient I/O between storage and memory and GPU memory, even if GPUDirect storage isn't enabled. It does this by falling back to the POSIX API to handle I/O between storage. That data gets read into CPU memory and then copied back into GPU memory. And while that doesn't avoid a bounce buffer through the CPU, it still is very, sorry. This compatibility mode is actually very important because you still need to get that data from storage into GPU memory efficiently. And if you don't have GDS, POSIX is going to be very performant for you. Better than using Python open to load in some data into some array structure and then copying it back to the GPU memory. So in order to evaluate this performance, I got access to the Acre cluster at Vanderbilt, courtesy of Andrew Mello there. He is responsible for making sure that this whole GPUDirect storage environment got set up correctly. Our test bench here involves a NVIDIA A6000 GPU And we are reading from a NVMe Samsung SSD, which connects into a liquid element add-in card via a 4th generation PCIe 4-pin connection. On the chart here, we have 3 main I/O APIs that we are trying to evaluate. In the solid lines, we have QuickIO using the CuFile API to perform GPUDirect storage transfers. In the dashed lines, that's when we are running QuickIO in compatibility mode, and we are instead reading through the CPU and then into GPU memory. And then on the bottom here, we have the dashed dotted line. That's just when we are reading in data using Python open and then copying that data to the GPU ourselves by calling CuPy.fromBuffer on the buffer objects. Interestingly enough, the promise of GPUDirect storage is that it offers high throughput, but at the expense of high latency, which would suggest that for small read sizes, we would expect GPUDirect storage to be slow, and we might want to use POSIX instead. But in our tests here, we actually see, so on the x-axis here, we have the read size, and it's logarithmic. So down here, 10 to the 6th, that's about a megabyte. And then all the way over here on 10 to the 9th, that's about a gigabyte. And we see for small read sizes on the scale of a megabyte, QuickIO in GDS mode was actually faster than POSIX mode. Then as the read size increased, eventually QuickIO's POSIX API ended up outperforming GPUDirect storage transfers. I should also explain the N threads here. So QuickIO internally will parallelize your I/O for you. And in my testing, what I saw was that when we're in GDS mode, increasing the number of threads beyond 2 didn't increase the throughput that we saw. Similarly, when we're in compatibility mode and using the POSIX API to perform the reads, going above 5 threads didn't offer any significant improvements. So then, how do we read the R-tuple binary and interpret that as data? As I stated before, R-tuple is purposely simple in its layout. We have clearly separated metadata from the payload data. And that metadata tells us how to locate, decompress, and deserialize the payload data. Then, the payload data itself is organized into a collection of clusters and pages. The clusters contain a collection of fields across a range of entries. And then within that cluster, we have pages. And the pages themselves contain the blocks of data for a field within a cluster. So in this example here, the variable jet mass is stored in pages 1 through 4, where pages 1 and 2 are stored in cluster 1, and then pages 3 and 4 are stored in cluster 2. So in the typical uproot workflow, when we are using the CPU to interpret the raw R-tuple data, we need to first locate and read a page of data. So using the file metadata, we will locate and read that data into CPU memory and represent that as a NumPy array in Python. Once we have that data, we will then use the page header to identify the compression algorithm and then decompress that array using CramJam. Once the array has been decompressed, we then perform deserialization operations, which are typically just byte-level manipulations on the decompressed NumPy arrays. Then this must be repeated on all the pages of data that the user requests for the fields that they need to analyze. And once we have all that read in and processed, we then reconstitute all those buffers into a singular array structure. And then if the user needs that data to be on the GPU, we will, as a final step, copy that into GPU memory. So now, in order to interpret R-tuple data on the GPU, we need to make some major changes. Since we have the raw data on the GPU, we cannot use these Python libraries to perform the decompression and deserialization. And additionally, since we are doing GPU interpretation, we open up ourselves for highly asynchronous and parallel processing. So again, using the file metadata, we will locate all the pages that we need. And instead of reading a singular page of data, decompressing and deserializing, we will just initiate asynchronous reads of all the pages needed that for the user is requesting. And then we will load that raw data into CuPy arrays in GPU memory using QuickIO's CuFile bindings. And then since we have to locate and read these pages, while we're doing that, we're able to access the decompression metadata, which we will store for later in a class object. So once we initiate all these asynchronous reads, we need to then synchronize with the device and make sure that everything has been properly loaded into the GPU's memory, and then batch decompress those arrays in parallel with QuikIO's NvComp bindings. Once we have decompressed all the data, we then again can queue up asynchronous deserialization operations of the decompressed CuPy arrays. Once we have queued up all these deserialization operations, we need to synchronize with the device before we then reconstitute all these buffers into a singular array structure for the user. And since all the data is already on the GPU, we do not have to do a copy as a final step. It has been a little tricky, though, to evaluate the performance of GPU interpretation versus CPU interpretation. This is because it is expected that at some scale, GPUDirect storage and GPU interpretation in general should offer some significant improvement over CPU interpretation. But it is unclear what that scale is or how to define that scale. This is because the payload data itself, the pages, are highly heterogeneous. So it's hard to come up with a clear answer as to when we should be using GPUDirect storage is like the best option. In some of my initial tests, so the results of this test were run on a slightly different test bench than what I showed, but at first we saw that when running KvikUproot in compatibility mode, so we weren't using GPUDirect storage, it was just the POSIX API, KvikUproot GPU interpretation was roughly 15% faster than Uproot's standard CPU interpretation. However, as the software evolved, we did some updates at Acre to CUDA, and there were some updates to the Uproot package. These gains came to parity, and GPU interpretation was no longer significantly faster than GPU interpretation. In spite of this, though, KvikUproot's GPU interpretation is still competitive with Uproot's CPU interpretation. There was many technical developmental challenges and also challenges in maximizing the performance of this package. Specifically because GPUs are by nature high latency, the page sizes of our tuple data is not GPU aware, so to speak. The QuikIO has a GDS threshold setting, and this is this point at which below the GDS threshold, it is expected that using the POSIX API should be faster because of the high latency. GPUDirect storage wouldn't make sense. But above 1 megabyte, QuikIO expects for the average user system, GDS should be faster. Interestingly enough, in our tests, we did see that just above 1 megabyte, GDS was faster than the POSIX API. But those gains at larger and larger read sizes disappeared. And actually, it's to a significant amount. So the page sizes themselves sort of limit us from really exploiting the throughput of GPU computing. And also, from a technical development standpoint, CuPy is not yet at a one-to-one drop-in replacement for NumPy. Plenty of NumPy's functions are implemented in CuPy, but some of them are missing. Specifically, in the development of QuikUproot, we use, or I should say, in the CPU interpretation of our tuple data, we use NumPy insert, which does not exist for CuPy. There is no CuPy insert function. That means you have to just write a trivial amount of code that can replicate the behavior of NumPy insert in your own programming. That means, many packages are going to have to write these functions for themselves over and over. And further, because you have this missing function, you need additional steering in your code to make sure that the correct function is called and you don't throw an error when you try to call CuPy insert, for example. More importantly than missing functions, the lack of support for CuPy structured arrays limits the range of function for GPU interpretation of our untupled data. When using CPU interpretation, all our untupled data can be interpreted by uproot. But since CuPy does not support structured arrays, we are not able to support all interpretation of our untupled data via the GPU. And it's challenging to communicate what sort of things users will be able to read. Since the users might not know already that in their data files, they need the support for structured arrays. There's also been some challenges when using QuikIO's NvComp bindings. At the scales that I have been testing, the QuikIO NvComp compilation at runtime is significantly longer than the decompression itself. During the first QuikIO NvComp decompression call, it must compile that CUDA code for you, and that compilation is orders of magnitude larger than the decompression itself. But either way, this isn't super, going forward, this is something that we won't be able to be working with anymore since QuikIO NvComp's bindings have been officially deprecated as of its latest release. Since there is already an officially supported NvComp, we haven't moved though to this official NvComp package because QuikIO's NvComp bindings actually has some functionality that the official package itself does not. In QuikIO's bindings, when you perform decompression, you can provide target output buffers for those compressed buffers to be decompressed into, which we actually exploit in the GPU interpretation. The official package does not support this. I have opened an issue and it has been internally documented, and NVIDIA promises that this will be targeted for a future release. Okay. So we do have some time for the demo, so that's nice. I'm going to try and convince you guys that we do have a true demonstration of GPUDirect storage that is transferring the data directly from storage to the GPU without first going through the CPU. I'm sort of going to do this in a hand-wavy fashion, though, because we do not have access to profiling results. CUDA does have a GDS stats profiler, and QuikIO would ideally work with this. But when you enable profiling at the configuration level, QuikIO crashes. It is not possible to profile QuikIO CuFile API calls in Python. But this has been promised that this will be fixed in CUDA 13. So in the meantime, I don't have access to the direct GDS IO stats, but I can show you the memory usage via NVIDIA SMI. So first, I'm going to show you what that looks like in the CPU interpretation. So as this is running here, we can see that the GPU, oh, that's probably really hard to see. Yeah. That's not working. Okay. The key point here is that, so around at this point, 13 seconds, this has been mostly the metadata parsing step for the CPU interpretation. And then as we get to the end, we see the memory usage suddenly spike all the way up to 736 megabytes. This is the final step where uproot copies the data from CPU memory into GPU memory. This picture is a little different, though, when you are using the GPU interpretation that QuikUproot provides. Okay. It's being weird. Okay. So this memory picture is a little bit different now. So pretty much the same here. We're going to start up our Python script, start running everything, and then around this point, we will see the memory usage across all 4 GPUs jump up to 270 megabytes. So this is the initialization step of CuFile. It is preparing all 4 GPUs for data transfer. So right now, all 4 GPUs are ready to take in data from storage directly. And then as a final step, we see the memory usage on GPU 1 as all the data is read into GPU 1 and processed and returned back to the user. And you can also, so on the last slide, the total memory usage was about 700 megabytes. So 270 plus the 700 gives us this 10,000. So uses a little bit more GPU memory when you're trying to use GPUDirect storage, but that can be kind of expected. So to wrap this all up in a bow, KvikUproot modernizes the high-energy physics data analysis pipelines by providing efficient GPU-aware I/O of R-tuple data. Using QuickIO and CuPy, KvikUproot provides GPU interpretation of R-tuple data, and that opens the door to end-to-end GPU acceleration in high-energy physics. KvikUproot is an essential development in keeping our analyses both fast and scalable going forward into the exabyte era. Thank you.
All right, thank you to the speaker. We have a couple questions here on Slack. First one is from Axel Donath. Does RN-tuple support hierarchical metadata? And is it compressed independently of the actual data?
I don't have the answer to that question, right? I should get that close. Andres, do you want to answer this question?
That's the metadata. I mean, so initially there was a plan to support like user-defined metadata, but right now, like that was scrapped for now, and they'll probably just implement it later on. That's all I know.
Thank you, Andres,
Thank you.
for tapping in.
All right, next question is from Nikolai Krug. Do you know any reason why would the direct storage mode ever be slower than a method where data has to go through the CPU?
So the question is, why at any scale should GPU direct storage be slower than going through the CPU? So this gets to the point that GPUs are high latency. So when you are doing GPU direct storage, the CPU is still steering the program. The CPU has to communicate to the GPU that the user wants to read some byte range. And then the GPU has to then talk to there's a driver that handles the memory mapping between storage and the GPU itself. So there's just a lot of overhead involved in transferring the data directly from storage into the GPU directly that isn't there when you are using the CPU.
My next question is kind of related to this. You mentioned performance does not improve beyond 5 threads. Is there a reason for that? Is it because of the reason you just mentioned, that GPU is being highly async, or is there another major parameter in the system that's getting saturated?
Yeah, so I haven't tested the explanation for it, because it's also kind of curious why, when you're using GDS, this peaks out at 2 threads, and when you're using POSIX, that peaks out at 5 threads. But clearly there is some sort of threshold where you are already saturated the throughput that you can get. So spawning more threads and making more calls isn't going to increase your throughput when you're already limited by other factors in your I/O.
Got it. Another question. Can you talk more about the hardware and software components enabling GPU direct storage?
Yeah, so GPU direct storage, as I said, involves many components. On the hardware side, only certain file systems are supported and certain forms of drives. Namely, there is support for NVMe, SSD, GPU direct storage, but that is not supported when reading from a hard disk. And there's also specific file systems that are supported, like ext4, and I think Lustre is another one that's supported. So you're only going to be able to utilize GPU direct storage if you meet those hardware needs. And then once you've met those hardware needs, you then need to go to the software side. So on the software end, I mentioned briefly that there is this driver that handles the memory mapping between the GPU and storage. On the surface, they cannot talk to each other. They don't know each other's memory addresses. And this driver helps them understand one another and see each other. And that needs to be set up. And that can actually be difficult as we ran into this problem at Acre, where we were having problems where the drivers weren't able to talk between storage and GPU memory.
All right, thank you so much.